All right, so good times. We're already to the Unit 3 exam, which means we're like 3/4 of the way through the semester, really, almost done. So the details for this exam, I've made it open 4 days, Monday through Thursday, because I know that, like me, people might be traveling for the 4th of July holiday. So hopefully sometime in that window, you can find a couple hours to sit down and take the exam. The good news is that that's all we have next week. I don't know if you've looked ahead to see what's on the calendar, but the exam is basically it. Like, once you get the exam done, then you can kind of just enjoy the rest of the week, sort of. The other thing that we have due next week is the collect and describe assignment for the project. Of course, you're welcome to keep sending those to me, and I can check those over, and you can get them done early in the week also, so that you can just kind of enjoy the week with your family or whatever with that. I did get one last night that I haven't had a chance to look at yet, but I will. So I can't remember if it's somebody from this group or not. I just saw an email right before I logged on that somebody had sent me theirs. Okay, so back to the test. There's 41 questions. There's 5 that are going to be kind of the, which method is this kind of questions like we had at the beginning of the last test. And overall, about 13-ish of the questions are review. So from units 1 and 2. So that's a good third of the test that's review and cumulative portion. So it would definitely be a good idea to go back and review all the unit 1 and unit 2 material. So I think the best way to kind of hit the highlights of that are watch the review videos from those units and look at the review group quizzes from those tests as well. So that would, I think that's lesson, I want to say it's lesson 8 and lesson 15 that are the review quiz, group quiz things for that. So there's a 4-hour time limit on this one, just like on the other ones, but it'll probably take you about the same amount of time as it took you to take the other exams. And you can have your 1 page of notes, your flow charts, if you'd like to print those out and have those handy, I'm fine with that. You can have Excel and the normal applet on the exam. So just in general, some of the general concepts that pop up a lot, I guess, on the exams are checking the requirements. And make sure that you're checking the requirements of the specific test that you're doing. So especially now that we've added proportions and all the different tests that go with proportions to our toolbox, then not all the requirements are, that n has to be at least 30. Like on our last test, that was the answer for most of the requirement things, but with proportions, it's different. So be sure that you're looking at the requirements for the specific test that it's asking for. So for test of means, like we said, then the populations must be normal or the sample sizes need to be larger than 30, except for analysis of variance, which is a little bit different, where you have to have normal populations. There's no sample size kind of get out of jail free card, and you have to have the equal variances. And then for test of proportions, you're going to be looking at, again, it depends on if you're talking about hypothesis tests or confidence intervals, whether you're going to look at n times p or n times p hat, and then n times 1 minus p, n times 1 minus p hat, all those need to be bigger than 10. And same thing in the 2 sample case, only now you're doubling all the things that you're checking. So it's kind of a bit more. And then, here's the exception. So for ANOVA, like we talked about, all the populations have to be normally distributed, and there's no either or option here. That's just it. Like, they have to be normal. And then all the variances need to be the same. But our rule of thumb for that is that the largest variance is less than 4 times the smallest variance. And just, I capitalized it here, but our rule of thumb involves the variance. My pen. Oh, maybe there it is. There it is. Involves the variance, not the standard deviation. So we looked at both things, variance and standard deviation, and variance is just the square of the standard deviation. So they're calculated very similarly, but it's important to just look at the word in here because the rule of thumb is different if you're looking at standard deviations. And then for chi-squared, we want all the expected counts to be at least 5 for the requirement. And kind of on the previous test, we'd really only talked about a couple of different distributions. I guess we talked about 3 by the last test. But now we've kind of talked about 4 different distributions that our test statistic might follow. So we have a normal distribution and a t-distribution, which are very similar to each other. They're both symmetric, bell-shaped, single-peaked. And then we've added the f-distribution and also the chi-square distribution, which are skewed distributions. They're both going to be skewed to the right, and but just, you know, kind of take note of the differences between the different distributions that we use that our test statistic follows. All right, so kind of more general concepts, thinking about writing the hypotheses. The null hypothesis is always going to have that equal sign in it. So even with our proportions problems that we've been looking at lately, then the null hypothesis still always has the equal sign. The alternative hypothesis is going to have different options. You can have greater than, less than, or not equals to, depending on what it says in the question itself. So read the problem, look at the context clues in order to evaluate what the alternative hypothesis should be. And the exceptions to those are going to be and chi-square. So the hypotheses for ANOVA are null hypothesis, all the means are equal. So in a sense, the null hypothesis still has the equal sign in it generally for that one. The alternative is the little bit different one, that at least one mean is different. And for the chi-square, we say variable 1 and variable 2 are independent for the null hypothesis, and the alternative is that variable 1 and variable 2 are not independent. So notice the wording here, because the wording is important. We say not independent, we don't say dependent. And there's a pretty good discussion in your textbook about why we word it this way. It seems like a fine line when you're writing it out, but it's an important distinction. So we have independent for the null and not independent for the alternative. When you're writing conclusions for your hypothesis test, our conclusions are going to be based on the p-value. The smaller your p-value, the greater the evidence against the null hypothesis. So we typically compare the p-value to alpha, our significance level. And if p is low, lower than alpha, then HO must go. So we reject the null hypothesis. So when we reject the null hypothesis, that means that we have sufficient evidence for the alternative. So this is almost like a formula that we can use to write the conclusions for any hypothesis test. And then when we fail to reject, failing to reject means that we have insufficient evidence for the alternative. So, and again, I know I mention this all the time when I do these test reviews, but I totally recommend if it asks you to figure out what the conclusion is, like don't even look at the answer choices. First, you know, use this template right here to just write out what you think the alternative should be, and then find the one that matches that in the list. Because usually there's like 6 options in the list, and there's very kind of minute differences between them. So it's easy to get confused, but if you write it down exactly how you know it's supposed to be and then match it up to the answer choices, that usually works the best. When we're writing conclusions for confidence intervals, and there was a couple questions like this on the last exam, there's going to be like 1 or 2 on this exam as well, that are a little bit tricky. So just remember that in general, we say, you know, we are whatever, 95% confident that the true mean, whatever you're measuring, so the true mean height of a BYU Idaho student is between 63 and 67 inches. So the correct way to write our conclusion is using the word confident there. So we do not want to use the word chance or probability when we're referring to a specific confidence interval. We also want to realize that our confidence interval is about the true value. It could be the true mean, or now that we're talking about proportions, it could be the true proportion or the true difference in the proportions, the true difference in the means. Again, just depending on what we're looking at. But it's about the population values. So there's nothing about individuals in there or other sample means or future sample means or anything like that. And the last point, our confidence intervals are based on a method that produces confidence intervals that contain the true mean whatever percent of the time, C% of the time. So if C is 95%, it is correct to say that 95% of 95% confidence intervals will contain the true mean. All right, so we're going to look at trying to see if we can guess some of these different methods. And oh shoot, I didn't set up the poll right, so we won't do the poll. We'll just have to take a guess. All right, so basically, and I don't think I put no, I didn't, the flow charts into the presentation, but basically how I think about these now, because we've kind of expanded, instead of just having the one flow chart like we did the last test, now we have two flow charts. One flow chart is when we're talking about means, which means that our response variable is quantitative. And the other flow chart is when you're talking about proportions, which means that your response variable is categorical. So the first thing that I ask now when I'm doing these questions is, what did I measure? What's my response variable? And is that response variable categorical or quantitative? So if it's quantitative, I know I'm dealing with means, and then I can go through that all the scenarios on the quantitative chart. So I'm going to ask one group, two groups, three or more groups, and then go down from there on the flow chart. If it's a proportion, so if it's categorical response, then it's going to be proportions, and I ask similar things. So I'm going to look at one group, two groups, three or more groups. Chi-square also looks at independence of two categorical variables, so we kind of throw that in there as well. So let's see if we can do a few of these. So the first one says, a survey was conducted by an investment house to see if residents of a small town had a good plan for retirement. They broke up the respondents into two categories, people without a college degree and people who had at least a bachelor's degree. Each respondent was asked if they had a plan for retirement. The investment house wants to understand the percentage of people with a college degree who have a retirement plan is different from the percentage of non-college grads with a retirement plan. Which hypothesis test should they use? All right, so first thing we're going to ask is, what are we measuring? And in this case, we're basically looking at whether or not people have a plan for retirement. So is that going to be categorical or quantitative? So you can hold up like a C or you can make a Q. What do you think? So yeah, categorical. So it's a categorical variable. So we know we're dealing with proportions. So are we looking at one group, two groups, or three or more groups? Two, perfect. So we were looking at people without a college degree and people who had at least a bachelor's degree. So no degree versus at least some degree. So we have two groups. We have a categorical variable, so that's going to lead us to two proportions. The nice thing about proportions is that there's not really as many further questions to ask once you get down to the one group, two group, three or more group kind of section, kind of done. Okay, next one. Scarlett works for a food magazine. She's reviewing the hottest new trendy dinner spot in town. The place is packed. She's interested in knowing if men and women prefer the same appetizers. She has a sampling tray and spends most of the evening passing out samples and asking the patrons which of the 5 appetizers they like best. She records the data and later will determine if the preference profile is the same for men and women. Which hypothesis test will she use? All right, so first thing we look at is our response variable. And we want to know if it's categorical or quantitative. So it says that she asked the patrons which of the 5 appetizers that they liked best. So is that going to be categorical or quantitative? Perfect, categorical, right? Because it's going to be like, oh, I like the shrimp wrapped bacon or bacon wrapped shrimp or whatever. So then we have to ask if we're looking at one group, two groups, or 3 or more groups. and kind of lumped in with the 3 or more groups. If we have 2 categorical variables and one of them has more than 3 levels, we're kind of just looking to see if they are independent, that's going to be lumped into that kind of 3 or more groups. So 3 or more options, I guess, kind of thing. So what do you think? 1 group, 2 group, 3 or more groups? Yeah, perfect. So we have the one variable, the appetizers, which has 5 levels. And then we have gender, which has the 2 levels. So since we have 2 categorical variables and one of them has more than 2 options, so 3 or more options, in this case 5, then that's going to make it the 3 or more groups, which means that we're doing the chi-square test of independence. Okay, next one. A botanist is developing a strain of tomato plants that is expected to yield larger tomatoes than existing strains. She needs to estimate the weight of the tomatoes produced by plants of the new strain. She grows a crop of the new strain, randomly selects 100 ripe tomatoes, and measures their weights. What type of confidence interval should she use? All right, so first thing we look at is what we're measuring here. And it says that she needs to estimate the weight. So weight is our response variable. Is that going to be categorical or quantitative? Any guesses? All right, yes, quantitative. So we have quantitative variables. So that means we're dealing with means. So then we have to look at whether we're looking at 1 group, 2 groups, or 3 or more groups. So how many samples did she take here? 1, 2, or 3 or more? I got some conflicting answers here. It says she grows a crop of the new strain and randomly selects from that 1 crop. So in this case, we have 1 group, just this crop of tomatoes of the new strain. So we just get 1 sample out of it. So then we have to ask if sigma is known or unknown. And there is nowhere in the problem where it says sigma equals. So since it didn't tell us what sigma is, then sigma is unknown. So sigma unknown. So we're going to do 1 mean with sigma unknown for this one. Okay, next one. Engineers creating a new kind of fabric select 36 swatches of the fabric and run them through a machine that simulates wear and tear on the fabric. 18 swatches are randomly selected to stay in the machine for 40 minutes. Another 18 are randomly selected to stay in for 50 minutes. Each swatch is given a quality rating from 1 porous condition to 100 perfect condition. Do swatches left in the machine for 50 minutes have a lower quality rating than those left in the machine for 40 minutes? All right, so first we look at what we're measuring, and it says each swatch is given a quality rating from 1 to 100. So is that going to be categorical or quantitative? All right, perfect. This one is quantitative. And the reason why it's quantitative, remember, if you're having a hard time deciding, then you ask, okay, is it a number? And in this case, yep, it's a number. It's a rating from 1 to 100. And would it make sense to talk about the average quality rating? And yes, it would make sense to talk about the average quality rating. So that makes this one quantitative. So that means we're dealing with means. So then we have to ask, are we looking at 1 group, 2 groups, or 3 or more groups? Yeah, 2 groups. So we have the group that stays in for 40 minutes and the group that stays in for 50 minutes. So if we have 2 groups, quantitative variable, now we have to decide if those groups are dependent, meaning that there was matching or pairing going on, or if they are independent, meaning that they were just randomly assigned to their group independently of each other. So I guess give me an I or a D for independent or dependent. Yeah, perfect. These are going to be independent because they just say that the 18 swatches were randomly selected from all the swatches. So if you're just randomly selecting some from a whole, then that's just, they're independent of each other. Like knowing something about the swatches that ended up in group 1 does not tell you anything about the swatches that ended up in group 2. So these are going to be independent. So we're looking at two means, independent samples for that analysis. All right, next one. A medical researcher studies a strain of E. coli to see how resistant it is to antibiotics. She prepares 50 cultures of the strain and subjects them all to a common antibiotic. After 48 hours, she classifies each culture as either viable or non-viable. She wants to estimate the true percentage of viable cultures. What type of confidence interval would be best for her to use? All right, so again, we start by looking at what is the response variable? What did we measure here? And it said that she classifies each culture as either viable or non-viable. So viable or non-viable, is that going to be categorical or quantitative? Yeah, absolutely. That's going to be categorical. So that means that we're dealing with proportions. So then we have to decide, can't spell proportions. We'll just say it's categorical. How about that? Okay, so we have categorical variable. We're dealing with proportions. And so we have to decide one group, two groups, or three or more groups. One, perfect. So it says she prepares 50 cultures of the strain. And also down here, it says she wants to estimate the true percentage, so just 1% of viable cultures. So that makes this one group. So we're going to do a test of one proportion. All right, here's another one. The Nellie Mae organization reports that the average credit card balance cardholders in the U.S. have is $5,134. The financial planner wants to determine whether the average credit card balance of cardholders from Rexburg is lower than this. The standard deviation for credit card debt is sigma equals 3,000. She takes a random sample of 100 credit card holders in Rexburg and finds that the mean of her sample is $4,578. Is there evidence of a difference? All right, so first we look at what it is that we're measuring. And it says that we're looking at credit card balance. So measuring credit card balance for individuals here. So is that going to be categorical or quantitative? Perfect. That's going to be quantitative. Money. It's money, so money's quantitative. So then we have to look at one group or two groups, or three or more groups. Yeah, we just got one group that we're looking at here. So, because it says she takes a random sample of 100. So we just have one sample that we looked at. So we have one group. So then we have to decide, do we have a known sigma or an unknown sigma? And if we look in the problem, look right here, it says sigma equals 3,000. So that means that sigma is known because they just told it to us. So this is going to be one mean with sigma known. And really, like, this is such a telltale sign right here. Like, even if like you ignore all the wording in the problem and there's a problem that says sigma equals blank, then you can pretty much automatically go to the one mean sigma known answer there. Okay, a marketing survey was done for Runner's World magazine. The marketing department wants to understand the preference of Nike running shoes versus Adidas running shoes. They have survey responses from about 1,300 runners. Furthermore, they asked the runners in the survey to self-identify as casual runners, moderate runners, or serious runners. They want to know if shoe preference and type of runner are independent. Which hypothesis test should they use? All right, so in this case, we're looking at shoe preference. So Nike versus Adidas. So is that going to be categorical or quantitative? Categorical for sure. And so then we have to decide if we're looking at one group, two group, three or more groups. Okay, and if we look at this one, it says, basically in this case, we have two variables that we're looking at. They're both categorical, but one of those variables has more than two levels because the type of runner that they are, we have the options of casual runners, moderate runners, or serious runners. So because this variable has three or more options, then we're going to end up doing a chi-square test. And something else that's kind of a giveaway on this one is the way that they word the question down here. So it says they want to know if shoe preference and type of runner are independent. So remember that when we're looking for independence of categorical variables, again, that leads back to doing the chi-square test. Okay, I think there's a bunch here. Okay, maybe I think we've done most one of all of them. Maybe we'll come back if we have extra time at the end. All right, so let's talk about proportions, since that's what we've basically been focusing on for this. Oh yeah, this is one. For this unit here. So suppose you wish to determine the proportion of on-campus students who will go home for Thanksgiving. You randomly select 120 students to participate in your study. Of those, 35 students are going home. What is the point estimate for the proportion of all on-campus students who will go home for Thanksgiving? So I think this word point estimate tends to throw people off. I feel like I get a lot of emails saying, "Let's ask for point estimate." I have no idea what it's talking about. The point estimate is just the sample value, basically. So in this case, because we're talking proportions, then the point estimate is going to be p hat, just the proportion of our sample who is going home for Thanksgiving. So we calculate the sample proportion by just taking the number of successes divided by the total number of observations. So in this case, that would be these 35 students over 120, our total sample size. So get out my calculator here. So I have 35 divided by 120 gives me 0.291. Well, if I was rounding to 3 decimals, it'd be 0.292. So that's it. That would be my point estimate for the proportion of students who would go home for Thanksgiving. So point estimate is just the estimate from your sample value. So p hat, or you can, x bar is a point estimate. So any number that's from your sample used to estimate the population value is a point estimate. So it says, considering the previous question, suppose that unknown to you, the real proportion of students who will go home is p equals 0.40. What are the mean and standard deviation of the sampling distribution for p hat? So remember, sampling distribution for p hat, that just says, okay, what would happen if we did this lots and lots of times? You know, so we keep taking samples, and from each of those samples, we calculate the sample proportion value. And we want to see how all those sample proportion values are distributed. So it's the distribution of the sample proportion, or it's also called the sampling distribution for p hat. So we know that the mean of the sampling distribution for p hat is equal to p, the population value. So in this case, that's going to be 0.40. Oops. And the standard deviation of the sampling distribution is going to be equal to the square root of p times 0.4 over n, which if we look back up at this problem, n was 120 total students were in our sample. So looking at that, I take 0.4 times 1 minus 0.4, so 0.4 times 0.6. Divide that by 120. It gives me 0.002, and then I'm going to take the square root of 0.002, which is 0.044721. And it just kind of keeps on going. So if I was rounding to 3 decimal places to enter this as an answer on the test, I'd put 0.0448. No, just kidding, 7. No, that's not 3 decimal places. Okay, I put 0.045. There we go. So there's 3 decimal places that I'd round to on the test. Now, just a word to the wise as far as rounding goes, especially when we're talking proportions, rounding too much or too soon can cause you big problems at the end of the line. So in a problem like this, where it just asked me for these two numbers, I would enter them like this. But if, and I think it does on the next screen, ask me a question that uses this value in it, I would not use the rounded value. I would use the value that has lots of decimals in it to do any additional calculations. Because rounding to the 0.045 and using that number could get you the wrong answer in the end. So this question says, what would be the probability that a random sample of 120 adults would have p hat less than 0.30? So our sampling distribution is normally distributed. So we're going to use the z-score for proportions to answer this question. So that's going to be equal to p hat minus p divided by that standard deviation of the sampling distribution that we just looked at. So that's p times 1 minus p over n. So the p hat I'm looking at is that 0.30 right there. And p, if you recall, here it is. On this page, it told us that p was equal to 0.40. So put 0.40 here. And then the denominator is just that standard deviation that we just calculated on the previous page. But here's where, instead of using that rounded 0.045, I'm going to use a whole bunch more decimals than that, because if I round to 0.045 right here, I'm going to get a different answer in the end. And I don't want to do that because it could be wrong. All right, so I'm going to take 0.3 minus 0.4, which is negative 0.1 for my numerator. And then my denominator, the same number I just calculated, but I'll just calculate it again here just to make sure I got everything right. All right, so again, I'm going to carry out a bunch of decimals this time. So I get 0.0447213595. I mean, that's probably overkill in the number of decimals I need, but, or if you can keep the number in your calculator, then that's even better, which is what I usually try to do. All right, so I end up with a z-score of negative 2.236. So I take that z-score to my normal probability applet, and I'm going to enter in negative 2.236 here. And if I look at the wording of the problem, I wanted to know p hat less than there. So I just shade everything to the left for less than of my z-score. So once I've shaded everything to the left, then that area up at the top is going to be my answer. So the answer is 0.0127, or if I rounded to 3 decimals, 0.013. So I will say that this was like the first lesson after the last exam, so it was the first one of this unit, and I think the concepts, when we start, we've looked at all these same concepts before when we talked about means, but they seem to be more difficult for people to grasp when we're talking about proportions. So I would recommend going back and looking at this chapter, and I did have a video that I sent out with this this lesson as well. I want to say it's lesson 10. Maybe it's not lesson 10. It's totally not lesson 10. That was back in the means. Okay, I can't remember what lesson number it is. But it was just the intro to proportions video that I sent out, whatever week that was, like 2 weeks ago. So so I recommend going back and looking at that again, because it'll kind of help refresh your memory on, because these are the problems that people frequently miss on the exam. Okay.
Sister Wilkinson, sorry, before you move on, do those absolutely have to be done by hand?
Yes, those do.
Okay.
There's nothing on the Excel worksheets to do this one. The Excel worksheets can do all your hypothesis tests and confidence intervals, but they're not going to do your probability calculations for you.
Okay.
Oh, sorry, I missed your question in the chat window.
That's okay.
Okay, so next up, We often judge people by their faces. Do some people judge candidates for elected office by their faces? Psychologists showed head and shoulders photos of the two main candidates in 32 races for the U.S. Senate to many subjects, dropping subjects who recognized one of the candidates to see which candidate was rated as more competent based on nothing but the photos. On election day, the candidates whose faces looked more competent won 22 of the 32 contests. If faces don't influence voting, half of all races in the long run should be won by the candidate with the better face. Is there evidence that the candidate with the better face wins more than half the time? All right, so if we were kind of evaluating this on what type of study this is going to be, then we look first at our response variable, and the response variable is like winning. So either you win or loss. So that's going to be a categorical type response, and we're just looking at this one group of candidates here. And so we have a one proportion situation here. So first thing we want to know is what are the null and alternative hypotheses? So first, just kind of a definitional term, P, our population proportion, would be the proportion of races won by the better face person. So they had all these candidates. They figured out by asking people questions ahead of time, like which one people thought looked better than the other one. And then they were trying to find out if the people that looked better actually won more of the time. So that's the purpose of this one. So P would be the proportion of races won by the better face. So our null hypothesis would be that it doesn't really matter what kind of face you have, then you're just as likely to win. So they say in the problem, if faces don't influence voting, half of all races in the long run should be won by the candidate with the better face. So half, when we're talking about proportions, is 50% or 0.50. So our null hypothesis would be P equals 0.50 for 50%. And then the alternative hypothesis, still going to be about P. We want to know if the better face candidate wins more than half the time. So more than is code for greater than. So we're going to use the greater than symbol there, and still the same number, the 50% in the alternative hypothesis. Okay, next we want to know if the requirements for this test are met. So if you look at the requirements for this test, this is a hypothesis test. So we want N times P and N times 1 minus P to both be greater than or equal to 10. Okay, he says, this question seems really complicated. It kind of sounds complicated when you read it, but then if you start thinking about what they're actually measuring, then it's not so bad. And I actually took this question from my textbook from my in-person classes, and I feel like the test questions are going to be a little bit more straightforward than this on the exam, if that helps you feel any better. All right, so the requirements for this test met. We want NP and N times 1 minus P to both be greater than or equal to 10. So in this case, N was 32. And the P that they're talking about here is going to be the P under the null hypothesis. So in this case, it's that 50% there. So when we're looking at this, N times P is just going to be 32 times 0.5, which is 16. Is 16 bigger than 10? Yes, so check. The other one, N times 1 minus P, so N is 32 times 1 minus 0.5. Remember that 0.5 just came from our null hypothesis. So that ends up also being 16. And 16 is still greater than 10. So both of those are bigger than 10, so we do meet the requirements. Now I did this by hand, but this is something that Excel will do for you, and I'll show you where to find it in there as well. Okay, so now we're ready to go ahead and do the test. And these tests can be done by hand, but I actually just recommend doing them in Excel. There's less room for error that way. So I think it's a great idea when you're learning the methods to do them by hand so you understand where the numbers come from that Excel is giving you. That helps with the conceptual understanding a lot. But on the exam, like, if you do it by hand, also check your answer in Excel and make sure that they match, because one thing about Excel too is that it doesn't do any rounding. So it carries out a lot of decimals. So you're going to get the best, you should get the most precise answer using Excel. Okay, but the key to using Excel, just like on our other exams, is just making sure that you're inputting the right things. So in this case over here, we need to put in X. X was the number of successes. So in this case, it was the number of races that were won by the better face candidate. And N is our sample size. So that was 32. So those numbers, they came directly from our problem. They're count numbers. They're going to be given to you right there in the problem. Next up, we have the hypothesis. So under our null hypothesis, we said that P was equal to 0.5, 50%, half. So we enter that value, that 50% right there. And then the type of test that we're doing goes along with the symbol in the alternative hypothesis. So if we've entered all of these things correctly, then we get all kinds of great stuff. So here's where it checks the requirements for us. This was a hypothesis test. So you can see it does those calculations, is the same calculations I already did. Does both of those calculations for us, which is super handy dandy. Okay, and looking for the test statistic and p-value, those are going to be right down here. So our test statistic is a z-test statistic, and it's going to be a one-sided p-value because we just had a greater than test. So it gives us the p-value right there. So again, you could do this by hand and use the normal applet to find these things, but Excel really makes it easy for us, so we don't have to do all that stuff. So based on this test, what can we conclude? Well, looking here, you can see that our p-value is 0.017. So it didn't give an alpha level, but a standard alpha level is 0.05. So if our alpha was 0.05, then we look at this p-value and say, is that high or low? Low, right? So when p is low, then HO must go. So we're going to reject the null hypothesis and conclude that we have sufficient evidence that the alternative is true. In this case, our alternative was that the proportion of races won by the better face is greater than 50%. So in other words, the better face candidate won more than 50% of the time. All right, so I'll write that down. So since we had a low p-value, that means that we reject H naught. Okay, rejecting H naught means that we have sufficient evidence for the alternative. And in this case, the alternative said that the better face candidate won more than half the time. So sufficient evidence that the better face wins more than 50% of the time. All right, so, what would be the take action part of this thing here? Well, if you're thinking about running for office, then maybe you should start by looking in the mirror, okay? And you don't have to be super duper attractive. You just have to be better looking than whoever you're running against to give you an edge in the competition.
Except in the case of Donald Trump.
Yeah, well, gosh, yeah. Some of our recent elections might not always help there. But it is interesting, like I read some book or something once that talked about how like Lincoln probably would not have been elected if he ran in modern day, because like back then there wasn't, I mean, there was newspapers, I guess, but people didn't see the candidates all the time. So it was probably more based on their politics, what they read about them, and they didn't find him really that attractive. So he might not have won if he ran today. But I think we've had a lot of ugly presidents, so I'm not sure that it always works all the time with the presidents. I don't think Clinton was attractive at all. So, all right. So next up, what's a 90% confidence interval for the proportion of races won by the better face? The key to remember on these confidence intervals is be sure to look at how confident they want you to be, because you have to fill that in. If you don't fill it in and go with the default, you probably will end up with the wrong answer. So in this case, 90%, so you enter in 0.90 right there where it says confidence level. And if you do that, then you get the confidence interval that you want. Okay, and then this of course is assuming that you've already entered in the X and the N previously. So if it's just a confidence interval question, you'd also have to enter in the X and N values up there too. All right, next example. Oh, sorry, I see there's like 3 messages on the chat. I'm not doing a very good job with that today. Oh, Carrie says, this question seems really complicated, so I've had issues with Excel rounding because it only shows 3 decimals. How many should I set them to? Okay, let me back up. These are both good questions that are on here. So, so Excel rounds when it shows it to you, but if you actually click on the cell itself and you look up in the little window on top, it'll show you the rest of the numbers up there. So as far as like entering your answer for like the confidence interval or the test statistic or something like that from the Excel numbers, then you're going to be just fine. But if you use some of these numbers in a calculation, that's when you'd want to get the non-rounded numbers. But when we do these tests and confidence intervals, we don't really need to do that. So it shouldn't be, the rounding shouldn't be that much of an issue. Okay, and Angela had asked, how can we multiply n times p and not times p hat for the requirements? And she already figured out the answer to her own question, which is that because it was for a hypothesis test. So in a 1 proportion case, the requirements are different. For a hypothesis test, you do n times p and n times 1 minus p. But if you're doing a confidence interval, then you do n times p hat and n times 1 minus p hat. So it can get kind of tricky. That's why I said, like, really on the exam, you know, make sure that you're looking at the requirements for the particular test that it's asking for, because there's quite a different variation in requirements for these. All right. Okay, so next example, a Pew Internet survey in 2012 examined several demographic variables of users of social networking sites. There were 846 men in the survey and 525 used social networking sites. Among the 956 women in the survey, 679 use social networking sites. Is there good evidence that the proportion of internet users who use social networking sites is different for men and women? All right, so looking at this one, the response variable here is whether or not you use social networking sites. So that's going to be categorical. And in this case, we're comparing men and women. So we have 2 groups. So we're looking at comparing 2 proportions. So first question, what are the null and alternative hypotheses for this study? So we're dealing with 2 proportions, which means we have a P1 and a P2. So we're going to have null hypothesis, P1 equals P2, because where does the equal sign always go? In the null hypothesis. And the alternative hypothesis, you don't have to have 1 and 2 as a subscript. You could have P men equals P of women or whatever. I just use 1 and 2 because it makes it easy. We just want to know if the proportions are different. So different is keyword for not equals to. So I want P1 not equal to P2 as my alternative. Are the requirements for this test met? And in this case, there's 4 things that all have to be bigger than 10. So we want n1 times p hat 1 and n1 times 1 minus p hat 1 and n2 times p hat 2 and n2 times 1 minus p hat 2 all to be bigger than 10. And we'll just check that in the Excel spreadsheet first. So they kind of do all the dirty work for us, and they tell you right here, hey, we want all of these to be bigger than 10. So all we have to do is look at these 4 numbers and say, yep, bigger than 10, bigger than 10, bigger than 10. We're good. So yes, we definitely meet the requirements. Then to do the actual test, then we're going to go ahead and enter in the numbers. So all these numbers here just came from the problem itself. So these 4 numbers here, the 846 men total, 525 that use social networking, 956 women, 679 use social networking. So we're entering in all those numbers here. And then we have to enter in the type of test. This is the one that people sometimes forget, which was not equals to in our case. And when we get those entered in, then we're going to get our test statistic and p-value down here at the bottom. So in this case, you know, we're into the conclusion part. Our p-value was 0. 0 is pretty low. So when p is low, HO must go. So we're going to reject the null hypothesis and conclude that we have sufficient evidence for the alternative. So looking back at my hypotheses, here's my alternative. So when I'm writing that conclusion, here's the conclusion. We're rejecting, P was low, so we reject H naught. We have sufficient evidence. Remember, reject always goes with sufficient. So sufficient evidence that, okay, and it was P1 not equal to P2. So if I was writing that in words, it would be the proportion of men who use social networking sites is different than the proportion of women. So we have sufficient evidence that the proportion of men who use social networking sites is different from the proportion of women who use social networking sites. And which one is bigger? Who uses social networking more? Well, that kind of information we can look right here at our p hats to kind of compare those. So p hat 1 was for the men and p hat 2 was for the women. So we show that they're different, and based on our p hats, we can say that women use social networking sites more than men do. Probably not that surprising. Well, maybe. Actually, I think my husband uses social networking sites more than I do. But he just uses them for different things, I think. Okay, and then what's a 99% confidence interval for the difference in the proportion of men and women who use social networking sites? And notice the wording on that. So when we're talking about proportions, 2 proportions, then our confidence interval is for the difference in proportions of there. So wording is a little bit different. Oh, going the wrong way. Okay, so again, we just need to make sure that we enter in the right confidence level here. And if we do that, then we'll get our lovely confidence interval down here. And again, this assumes that you've already entered in the X's and N's from the problem. But if you haven't previously done a problem, then a hypothesis test on that same data, then of course you have to enter those in. All right, last example here. In a general social survey, asked this question: have you attended religious services in the last week? Here's the responses for those whose highest degree was high school or above. Is there a relationship between education and church attendance? So this is a case where we have 2 categorical variables that we're looking at. We're looking at highest degree held, so level of education, and whether or not people attended church services. And one of those variables has more than 2 levels. So we're going to end up doing the chi-square test. So we want to know, what are the null and alternative hypotheses? So this is, remember, we write this a little bit differently. So null hypothesis is that the column variable and the row variable are, or variable 1 and variable 2, however you want to call them, are independent. So in this case, we would say education and attending church are independent. And the alternative is that they are not independent. So alternative, education, and attending church are not independent. All right, then we have to calculate the test statistic and the p-value. So to do this, we have to enter in the data into Excel here. And the key is, and I think some of you found this out on the homework, and this, my table up here doesn't have any totals, but if your table gives you totals up here, and they do those calculations for you, either row or column, then those numbers do not get put into this table that you're putting into Excel. So only the actual count data, not any summary counts, are going to go into the actual table. And you can kind of tell how many numbers you should be entering into this table if you just say, okay, well, how many options were there for education? Well, there were 4. And how many options were there for attending church? Well, there was 2. So if I take 4 times 2, that equals 8. That means that there's 8 numbers that I'm going to have to enter into this table down here. So I enter those numbers in just exactly like they are in the table up there. And that's all I have to enter. So if I can just get the data entered correctly, then it's going to give me the test statistic. So the test statistic for this test is the chi-square test statistic. In this case, it has 3 degrees of freedom and a p-value of 0.0027. To check the requirements for this one, the requirements are that all the expected counts are at least 5. So the expected counts are going to be given in this table under here. If you look on the row for expected, you just want to verify that all of those numbers are at least 5. So in this case, all these numbers, we have a big sample size here, so they were well over 5. So we do meet the requirements. And our conclusion, p-value is 0.0027, so that's very, very low. When p is low, HO must go. I guess all of our examples we rejected today. So we're going to reject. When we reject, that means that we have sufficient evidence for the alternative. So we have sufficient evidence that church attendance and education are not independent. And that's it. Okay, so here's just a few other things that I would recommend looking at before you take the exam. And I've talked about some of these already in here, but look at the Intro to Proportions video from, oh, here it is, lesson 16, the lesson number I couldn't remember earlier. Because like I said, I think people struggle with those concepts when they're first introduced, and then by the time you get to the test, you've kind of forgotten some of those things. So definitely go over those again, because there will be a few questions that use that information. Then I would also recommend completely reviewing lessons 10 and 11, which was just the introduction to hypothesis testing and confidence intervals. So we've kind of learned how to go through the mechanics of those, and I think a lot of people feel like, okay, I can do this. But there's still some concepts that are involved with hypothesis testing and confidence intervals that it goes over in lessons 10 and 11 that I think would be helpful to know on this test. And then just review how to write the hypotheses and how to track the requirements for all the different tests that we've talked about so far. So, and we have quite a few. You can look at the flow chart so you can see all of them. They're all listed on there, but we have 1 mean sigma known, 1 mean sigma unknown. We have 2 means independent. We have the 2 groups but paired data, so dependent. We have analysis of variance. Then we have 1 proportion, 2 proportions, and chi-square. So I think that means we're up to like 8 different tests that we have. So just be sure that you can write the hypotheses and check the requirements for all those tests and know how they're different from each other. And then, you know, when we covered the central limit theorem, I told you it was like the most exciting and important theorem of the entire semester. So I'd certainly recommend looking back at that one because we haven't really specifically talked about it in a while. And the central limit theorem often gets confused with the law of large numbers. So just kind of looking at both of those and trying to remember the differences between them so you could identify either or would be a good idea. And I did talk about those in, I think it was the very first test review video as well, on how to kind of distinguish between those. So if you're going back and watching those test review videos, you'll hit some of this information also. All right, that is all for this review. Does anybody have any questions or anything that they want me to answer? Sorry, Shelby, you're talking, but you're muted.
I know, I was saying I have a question, but you can't hear me. And all of my hands are full. On the group quiz, let me pull it up. For lesson 18, the group meeting quiz on question 6, my faithful group tried to explain to me how we got this answer, but I don't really understand how we got the answer.
Okay, let me see if I can pull it up. It'll take me a second. And I saw somebody else posted a question in the chat window that also relates to one of the homework questions or something. So let me get, let's see if I can get it all. I can get logged in and pull it up.
Wait, it actually might have been number 7. Hold on, let me check really quickly.
You're allowed to change your mind.
Okay. I need to go back and look at which one we got wrong. Okay. So many quizzes.
I know, now that we're getting close to the end of the semester, there's a bunch of stuff. It's kind of nice though when you have like fewer things to complete than you've already completed.
That's true. It was question 6 on the group quiz for lesson 18.
Lesson 18. Okay, let's see. Let me share that here. Okay, so you said question number 6?
Mm-hmm.
Okay, so this gives us this data up here. Let P1 be the proportion of females in the population who can taste PTC, and let P2 be the proportion of males in the population who can taste PTC. The research question for this study is given here: is the proportion of females who can taste it different than the proportion of males who can taste it? So question 6 says, what's the point estimate for the 95% confidence interval? So the point estimate is going to be the value from your sample that estimates what you're trying to estimate. So we're trying to estimate P1 minus P2. So from our sample, we're going to look at P hat 1 minus P hat 2. So up here, we find P hat. Let me see if I can turn on my pen here. Okay, so it says P1 is the proportion of females that can taste it. So P1 would be 52 out of 70, which is 0.742857. 0.742857. So P2, this is P hat actually, P hat 2. So the value from our sample of males that could taste it, there was 42 out of 59 males that can taste this. So 42 divided by 59 gives me 0.71186. 4. All right, so the point estimate down here then, for our question was the point estimate is I'm just going to take p hat 1 minus p hat 2. So if I take p hat 1 minus p hat 2, that's just going to be 0.742857 minus 0.711864, which gives me 0.0309927, whatever. So this would be the point estimate here. It's just the difference in those sample values. Does that make sense?
Yes, it does.
Cool. Good. Okay, let me look back at the question that, stop sharing me that. Okay, one of the homework problems for lesson 20, I got p equals 1. This seems totally wrong, but is it possible? It's probably wrong. If p equaled 1, that would mean that 100%, well, p is a population value. So that would mean that every single person in the population did it exactly the same. So that's, you know, like every single person in the population has blue eyes or whatever. So it's not very likely to happen like that. Your sample, if your sample is too small, it could be that you had p hat equals 1. Do you remember what problem number it was, Carrie?
I think it was 27.
Okay, let me see if I can find it.
I mean, I assume that I've just put in some numbers wrong into the into Excel, but I didn't have a chance to go back and figure it out. But I was like, p equals 1 doesn't seem right.
Yeah, and I'm pretty sure it's wrong, but we'll look at it. It just depends. Okay. So you're talking about like is it on the group meeting quiz or is it like in the individual preparation? Because there isn't actually like a homework problem for lesson 20. Okay, so is it one of these in here? What number did you say you thought it was? Carrie, what number did you think it was?
37.
37. Oh, p-value. So you're talking about p-value.
Yeah. Right.
Study was done to test the notion that people are taller when they first wake up in the morning. Bed, to test this. Values were recorded. You want to determine if children are taller in the morning and the evening. Open up the file. Get the mean differences. So it is possible if the sample value is equal to what it is under the null hypothesis and it was a two-sided test, then you could get a p-value of 1.
Okay.
So if they're looking at the differences of those, was the difference 0? Do you remember the sample value? Was the sample value difference 0?
It was. They were all different, so there was no 0. So I didn't know what I could have done wrong to get a 1 in, like, because I just, I copied the data from the AM/PM heights into the Excel sheet and P equaled 1, so I wasn't sure. Yeah, I didn't know how I could do it wrong, but that it must have been wrong.
Right. Well, I will take a look at that, and I'll